Welcome back. We will be mainly talking about relations, and in particular we'll be talking about the equivalence relations. So first let's start with this definition. Given two sets S and T, define S cross T to be the set of all ordered pairs XY where X is in S and Y is in T. The reason I'm using the word ordered pairs is because X comma Y is not the same as Y comma X. This is this collection of ordered pairs XY where X is in S and Y is T. The set S cross T is called the Cartesian product of S and T. Here's an example. Let's say I have the set A with the elements 1, 2, 3 and the set B with elements 4, 5, and 6. Then what is A cross B? Well, we have to pair up each element of A with each element of B. So we get 1, 4, 1, 5, 1, 6. 2, 4, 2, 5, and 2, 6, 3, 4, 3, 5, and 3, 6. Okay, so this is A cross B. Notice that the number of elements in A cross B is 9, which is 3 times 3. So if we multiply the number of elements of A with the number of elements B, we get the number of elements of A cross B. And the reason is that you can do a counting argument here is because we are trying to count the number of pairs where the first coordinate is coming from A and the second coordinate is coming from B. So for the first coordinate of the pair, we have 3 possibilities, and for the second coordinate of the pair, we have 3 possibilities. So we have a total of 3 times 3 possible pairs. Okay, so now the definition of a relation. Let S be a set. A subset R of S cross S is called a relation on S. We will write A tilde B to denote the fact that AB belongs to the relation. So what is the relation again on a set S? Well, on a set S, a relation on a set S is just a subset of S cross S. So R is a subset of S cross S. So that's what a relation is. So whenever the pair AB belongs to the relation, we write A tilde B. Or sometimes we write ARB. For example, let's take the set B to be 1, 2, 3. Then I can take the following subset of B cross B. So 1, 1, 1, 3, 2, 2, 3, 1, 3, 3. So clearly R is a subset of B cross B. So R is a relation on B. Here is another example. Here we are defining the following relation on the set of real numbers. So we are defining a relation on the set of real numbers. We're saying that X is related to B, X is related to Y, X tilde Y, if X is less than or equal to Y, for all X, Y in R. So what pairs are we picking? So this is the set of all pairs XY in R cross R such that X is less than or equal to Y. That is, the first coordinate is less than the second coordinate. Now, as a geometric object, what is that? So R cross R is the plane, the set of all points in the plane, and then Y is equal to X is a straight line passing through the origin with slope 1, And then, so since y is greater than x, it means we want all the points above the line y is equal to x. If you take all the points above the line y is equal to x, then all those points will belong to this relation. Here are some silly examples. Let's take S to be the set of all people. We define the following relation on this set S. For all AB in S, we define that A is related to B if A and B are siblings. So that's a relation. So we're saying that the pair AB belongs to the relation if A and B are siblings. So that's the relation on the set S. If I take S to be the set of all males, and then we define that for all AB in S, A is related to B if A is the son of B. So the pair AB belongs to the relation if the first coordinate A is the son of the second coordinate B. Okay, so now we define what is called an equivalence relation. An equivalence relation on a set S is a set R of ordered pairs of elements of S. That is, R is a subset of S cross S such that the pair AA belongs to R for all A in S. In other words, A tilde A, or A is related to A for all A in S. This is known as the reflexive property. The second condition for a relation R to be an equivalence relation is that if AB belongs to the relation, then so does BA. In other words, if A is related to B, then B must also be related to A for all AB in the set S. This is known as the symmetric property. Now, property number 3 says if AB is in the relation and BC is in the relation, then AC also belongs to the relation. That is, A tilde B and B tilde C implies that A tilde C for all A, B, C in S. This is known as the transitive property. So a relation R on S, remember, it is just a subset of S cross S, and we call it an equivalence relation if it satisfies these three properties. That is, if the relation is reflexive, symmetric, and transitive, then we call that relation an equivalence relation. Let's explain this definition with examples. Let's say S is the set of all people, and the relation is the following: A is related to B if A is a sibling of B. That is, the pair AB belongs to the relation if A and B are siblings. Is that an equivalence relation? Well, notice that this relation would be reflexive because certainly if I define siblings to be, two people are siblings if they have the same father, well then if I use the definition, then of course A is related to A because A and A, they have the same father. So that's reflexive, and then it's symmetric because if A is a sibling of B, then B is also a sibling of A. So we see that this relation is a symmetric relation. And then the transitive property, also holds here, because if A is the sibling of B and B is the sibling of C, then A would be a sibling of C as well. So in other words, if A tilde B and B tilde C, then A tilde C will hold. So this relation is a transitive relation as well. Okay, another example, let S be the set of all people. For A, B in S, define the relation A tilde B if A is the spouse of B. Certainly this is a symmetric relation, but it is not reflexive, or it is not a transitive relation. Another example would be if S is the set of all people. So the relation in example 2 here is not an equivalence relation. Let S be the set of all people again, and for A, B in S, define the relation A tilde B if A is a child of B. Clearly, it doesn't satisfy the symmetric, transitive, and the reflexive properties, because if A is the child of B, then B is not the child of A, so that's not symmetric. A is not a child of A itself, so it's not reflexive, and it's not, you can check that it's not transitive either. So I hope this example clarifies the definition of an equivalence relation. Here is another example. There are two examples here, in fact. The first example said, in the first example, we have the set of all triangles in the plane, and we are defining that if A and B are triangles, then A is related to B, A tilde B, if A and B are similar. Remember, similar means that they have equal angles. Then this is an equivalence relation, because if clearly A is similar to itself, a triangle is always similar to itself because they have the same angles. If A and B have the same angles, then B and A have the same angles. So if A is similar to B, then B is also similar to A, so it's symmetric. And the transitive, if A is similar to B and B is similar to C, then the triangle A would be similar to C as well. That is, if the angles of A and B are the same and the angles of B and C are the same, then the angles of A and C must be the same. So the first relation is an equivalence relation. Another example here is the set of all, S is the set of all polynomials with the real coefficients, and for polynomials f, g in S, define f tilde g if f and g have the same derivatives. So this is also an equivalence relation that you can check, because clearly f is related to itself because f and f have the same derivatives, and it's a symmetric relation because if f and g have the same, if the derivative of f and the derivative of g are the same, then the derivative of g is the same as the derivative of f. So if f is related to g, then g is also related to f, clearly. And the transitive property holds because if f is related to g, that is, if the derivative of f is the same as the derivative of g, and the derivative of g is the same as the derivative of h, then the derivative of f must be the same as the derivative of h. So we see that this relation here must be a transitive relation as well. So we conclude that this relation is an equivalence relation. Here are two exercises on proving that a given relation is an equivalence relation, and I'm going to stop the video here. In the next video we'll be talking about equivalence classes.